Okay, just a quick pause. Here is an updated image of our simple network. And in the previous section, we talked about some of the most common devices inside of a network, such as switches, routers, and modems. We also mentioned that there are two main identifiers for each device inside of a network. We mentioned that those are MAC addresses and IP addresses. Now, while we did discuss about MAC addresses, IP addresses are something that we will talk about later in the course. Now, one more thing that we want to talk about in the course is how exactly these devices communicate. How do they transfer and share data? Well, those are the questions for the future lectures. For now, we are introduced to common network devices as well as MAC addresses. Now that we got that out of the way, let's go into the next section where we're going to talk about some of the most common network topologies out there. Alright, let us briefly describe different network topologies. We will start with one of the most common network setups, which is called star network or star topology. Now, in a star topology network, every node connects to a central network device, which in this configuration could be something like a hub, a switch, or a computer. The central network device acts as a server, and the peripheral devices act as clients. Now, each device on the network has a dedicated connection to the hub, which essentially creates a structure that resembles a star, and therefore it's called star network or star topology. Now, some of the key components of a star network would include central hub, and the central hub is typically, once again, a network switch, and it serves as the focal point of the network. It manages and controls the data traffic between connected devices. Another key component are nodes, which are individual devices or computers connected to the central hub. These can include things like computers, printers, servers, or any other networked device. Now, here are some of the advantages of a star topology network. Star topology network has centralized management of the network through the use of the central computer, hub, or switch. It is also easy to add other computers to the network, and if one computer fails or stops working, the rest of the network continues to function normally. However, some of the disadvantages would be that it may have a higher cost of implementation, especially when using a switch or a router as the central network device. Now, the central network device determines the performance and number of nodes that the network can handle. If, however, the central hub or switch or computer fails, the entire network goes down and all computers are disconnected from that network. Alright, that would be some basic important stuff regarding star topology networks, and now let us discuss bus topology in the next lecture. Alright, bus topology network. A bus topology is a network configuration in which all devices are connected to a single central cable, which is called the bus. This cable acts as a communication pathway and data travels along it, passing through each device on the network. Now, each device on the network is equipped with something called network interface card that allows it to capture and process data packets that are relevant to it. Some of the advantages of bus topology would be that it is the easiest network topology for connecting peripherals or computers in a linear fashion. It works very efficiently when there is a small network. Now, the length of the cable that is required is less length than in a star topology. Another benefit of this topology is that it is easy to connect or remove devices in this network without affecting any other devices. It is also very cost-effective as compared to other network topologies. The bus topology, however, has lots of disadvantages, and these would be that bus topology is not so great for larger networks. Also, identification of problems becomes very difficult if the whole network goes down. Same goes for troubleshooting individual devices, which also can be very hard to do so. Now, one important thing about bus topology is that it needs terminators which are required at the both ends of the main cable. And the reason why it is so good in a small network is because additional devices can slow the network down, so the larger the network, the worse the topology works. And also it's important to note that if the main cable was to get damaged, the whole network would fail. And last thing that we want to mention about bus topology are its key components, which include central cable or bus. And we already mentioned that the central cable is the backbone of the bus topology. It runs through the network, connecting all devices to a single communication line. And we also have terminators, which we mentioned. Terminators are located at the end of the central cable. They are used to prevent signal reflection and ensure that data does not bounce back and create interference. And last, we have nodes, and nodes are simply devices connected to the central bus cable, which include devices like computers, printers, and other networked devices. A ring topology is a network configuration where devices' connections create a circular data path. Each network device is connected to two others like points on a circle. Now together, devices in ring topology are called a ring network. And inside of a ring network, packets of data travel from one device to the next one until they reach their destination. Most ring topologies allow packets to travel only in one direction, which is called a unidirectional ring network. But others may permit data to move in either direction, which would be called bidirectional. Now, some of the advantages of ring topology would be that usually all data flows in one direction, reducing the chance of packet collisions. A network server is also not needed to control network connectivity between each workstation or device, and data can transfer between these workstations at very high speeds. It's also important to note that additional workstations can be added without impacting performance of the network. Some of the disadvantages, however, would be that all the data that is being transferred over the network must pass through each workstation on the network, which can make it slower than a star topology. The entire network will also be impacted if one workstation shuts down. And it's important to note that the hardware needed to connect each workstation to the network is quite expensive. Now, some key components of a ring network would be nodes, which are once again devices such as computers, servers, or network peripherals that are connected to the ring and that are responsible for sending, receiving, and processing data. And we have the ring, which is the circular communication pathway which is formed by connecting each node to its neighbor inside of a loop. And data packets travel around this ring. Now we also have something called multi-station access unit. In some implementations, a multi-station access unit is used to connect devices to the ring. It acts as a hub to facilitate communication between devices. Okay, we got two more to cover, which are mesh topology and hybrid topology. Mesh topology is a network configuration in which each device is directly connected to every other device, creating an extensive web of interconnected links. Now, there are two primary variations of mesh topology. We have full mesh and we have partial mesh. Now, in a full mesh topology, every device is connected to every other device on the network. This configuration results in a high degree of redundancy, but also requires a significant number of connections, especially as the network grows. In a partial mesh topology, devices are not connected to every other device, but they do maintain selective connections based on their specific requirements. This reduces the complexity of connections while retaining redundancy. Now, some advantages of mesh topology are high reliability, redundancy, scalability, fault tolerance, and security, while the disadvantages are complexity and cost, as well as bandwidth consumption, since in a full mesh topology, the numerous direct connections between devices can lead to increased bandwidth consumption. Now, key components of a mesh topology are nodes, which are devices like computers, servers, or network peripherals, which are interconnected with one another through direct links. And we have links, which are physical or logical connections between devices, such as wired or wireless connections. Alright, one last topology to cover, and that is hybrid topology. See you in the next lecture. Okay, hybrid topology. Can you guess what that is? Well, if you guess that it is a mix of already existing topologies, you were 100% right. A hybrid topology is a network configuration that combines two or more different network topologies into a single integrated network. This allows organizations to harness the advantages of various topologies while mitigating their respective drawbacks. Now, the choice of which topologies to combine depends on the specific needs and objectives of the network. Some key components of hybrid topology would include nodes, which are once again devices, computers, servers, printers, or network peripherals that are part of the network. And another key component would be the multiple topologies, which are actually the primary components of hybrid topology, and they are just various network topologies that are integrated for network to work. Now, common topologies combined in hybrid networks include star, bus, ring, and mesh, and some common combination types of hybrid topologies would include star-ring hybrid topology and star-bus hybrid topology. And let's also mention some of the advantages, which are that this type of topology combines the benefits of other types of topologies into one single network. This can of course be modified as per requirement, as it is extremely flexible and it is very reliable. Also important to note that it is easily scalable, as hybrid networks are built in a fashion which enables easy integration of new hardware components. Now, even though that hybrid topologies are mostly used in larger networks and they handle a large volume of traffic, error detecting and troubleshooting are rather easy to do. However, the two main disadvantages of hybrid topologies would be cost of implementation and complexity, since managing and maintaining a hybrid network can be complex, as it involves dealing with multiple topologies and ensuring their seamless integration. And logically, the cost of implementing a hybrid network can be higher than using just a single topology due to the combination of different components needed. Alright, that would be about it regarding network topologies, and in the next section we're going to talk about IP addresses, what different types of IP addresses are there, subnetting, and we're also going to show some networking commands that you can run from your PC at home. See you in the next lecture. Alright, IP addresses. We already know by now that each device connected to the internet has its own IP address. Now, remember when we talked about MAC addresses and how they are unique? Well, we can't really say the same for the IP addresses. This is because we can divide IP addresses into local or private and global or public IP address. Now, local or private IP addresses are something that you see inside of your network. They will only work within the network itself, and they're not used to route traffic outside your network. Typically, your router will have both private and public IP, where private IP will be for inside the network, while public IP will be used to route traffic through the internet. The private IP addresses are given to you by DHCP, which is Dynamic Host Configuration Protocol, and they are not unique since they are the same in lots of networks or in lots of local area networks. There are three main types or three main ranges of private IPs that we should be familiar with, and that is Class A, Class B, and Class C, and you can take a look at their ranges right here on the presentation. Now, you will most commonly encounter Class C in home networks, and this is the one with the range of 192.168.something.something. You can check for yourself right now to see which range does your device belong to inside of your network. If you're on Windows, open your command prompt and type ipconfig, and if you're on Mac or Linux, open up your terminal and type ifconfig. Now, we should also be familiar with subnet masks. A subnet mask is a 32-bit value that is used to divide an IP address into two parts: the network address and the host address. It is used to determine which portion of the IP address represents the network and which portion represents the host. We have these three classes of subnet masks: Class A, Class B, and Class C. And you might notice that, same as IPs, subnet masks are split into 4 octets, and each octet has 8 bits. The left part of the subnet mask is for the network, while the right part is for the hosts. So for example, if we have 255.255.255, the left 24 bits are for the network, while the right 8 bits will be for the host itself, or for the hosts. Now, it's also important that we are aware of different types of IP addresses besides just private and public IPs. You might have also heard about IPv4 and IPv6 addresses. The ones that we just talked about are IPv4 addresses. An IPv6 address, on the other hand, are in hexadecimal format, and they are 128-bit addresses. You can already figure that there are many more IPv6 addresses than there are IPv4 addresses, and that is exactly the reason as to why they were created. We were running out of IPv4 addresses, so we needed a different way of IP mapping devices. First 64 bits on the left side of the IPv6 address are for the network, and other 64 bits are for the host. When it comes to IPv6 addresses, we have many different ranges of addresses, but here are the main ones that you should know. We have public IPv6 addresses, which can be used externally, and these public addresses will start with 2001, 2002, or 2003. Now, same way that IPv4 has local addresses, well, so does the IPv6. These local IPv6 addresses start with FE80. We also have unique local IPv6 addresses, and these start with FC00 or FD00. And also, since an IPv6 address can be quite long, there is a method of simplifying IPv6 address by removing zeros. So here we have an example of IPv6, and we also have an example of how simplifying it with removing zeros would look like. As you can notice, we used double column instead of all of these zeros, but it is important to note that this can only be done once. We can only use the double column once. So if you, for example, have multiple blocks of zeros in an IP, we can exchange the first block with double column, but the second block we must write as column, 0 column, and not just double column. Okay, that would be the basics of IP addresses. We talked about private and public IP address, and we also talked about IPv4 and IPv6 addresses. Now that we know that, in the next lecture, let's talk about protocol, which we mentioned earlier, and that is DHCP. Okay. Let's quickly talk about subnetting and subnets. Now, this can be confusing for beginners sometimes, as it is considered a bit more advanced. However, we will still mention it and explain it as best as we can. So, what exactly is a subnet? A subnet can be defined as a logical subdivision of an IP network. Subnetting, on the other hand, is the process of dividing a network into 2 or more networks. There are many benefits of subnetting, such as, for example, security and improving network performance, but how exactly is it done? Well, we talked about subnet mask in the previous lecture, and remember that we mentioned terms such as network ID and host ID. And in the last lecture, we showed subnet mask that looks something like this. So 255 192.255.255.0. Well, there is another way that this subnet mask can be written, and it looks like this, /24. And before you ask any questions, I have a table ready that you can follow along to figure out the subnet mask notation. So the table looks like this. We have 3 rows, which are subnet, host, and subnet mask, and we have several columns depending on how many subnets are there. So if there is, for example, 2 subnets inside of a network, each of those subnets will have maximum of 128 hosts. And the notation for those 2 subnets would be /25. And if, for example, we had 16 subnets, there will be 16 hosts per subnet, and the subnet mask notation would be /28. So let's say that we, for example, have a network ID of 192.168.1.0/24. This would simply mean that this network has 256 hosts available. Now, typically your home network will have this type of subnet mask if subnetting has not been done yet. So, for example, if we look at the previous table, and let's say that we were given network ID of 192.168.1.0/24, and we are required to create 8 subnets from that ID. We would choose the 4th option in the table, which is 8 subnets, where each of those subnets would have 32 hosts, and those 8 subnets would have a subnet mask of /27. Let us look at that in a new table. So let us find out network ID, subnet mask, host ID range, and number of usable hosts, as well as broadcast ID of the example that we mentioned. So let's say the example again. We're given the network ID of 192.168.1.0/24, and we are required to create 8 subnets from that network, as well as fill in each subnet information inside of this empty table that we see. So first of all, we already said that each subnet mask will have /27, which we simply just read from the previous table. We can also read the amount of hosts, which would be 32 for each subnet. The network ID of the first subnet will be the same as our given network ID, which is 192.168.1.0. However, for the rest of the network IDs, we have to add additional 32 hosts each time. So, for example, the second network ID will be 192.168.1.32. The third network ID will be 192.168.1.64, and so on, up to the 8th network ID, which will be 192.168.1.224. Okay, so we got the network IDs, and we got the subnet masks of all 8 subnets. Now, to calculate the broadcast ID, we can use the equation of the next network's ID last octet minus 1. So just to make it clear, the broadcast ID for each subnet would look like this. And we have the equation down below. You just take the next network's IDs. For example, if we are taking a look at the 3rd subnet, which has the network ID of 192.168.1.64, its broadcast ID would be the next network's ID, which is the 4th one, which has the ID of 192.168.1.96 minus 1, and that results in 3rd subnet's broadcast ID being 192.168.1.96 minus 1, which is 95. Alright, and we also need to fill in the host ID range, which is range between network ID and broadcast ID, which for the first network would be 192.168.1.1 up to 192.168.1.30. For the second one, it would be from 192.168.1.33 minus 192.168.1.62. And you can see for all the 8 subnets how the range would look like. So it is written in the table right now. Now, last thing that we want to fill in is the usable amount of hosts. So don't confuse the amount of hosts with usable amount of hosts. We know that each subnet has 32 hosts. We already saw that from the previous table. But if we remove the network ID and broadcast ID, we get that each subnet has 30 available hosts. The formula for calculating available hosts looks like this. So the total number of hosts in a subnet minus 2. And you can always read the total amounts of hosts in a subnet from the first table that we showed inside of the lecture. Okay, this one might have been tougher than last lectures, but make sure to rewatch it a couple of times if needed, and I'm sure that you will get it. Nonetheless, thank you for watching, and I will see you in the next lecture. Welcome back. Let us take a look at some of the basic networking commands that you can run on your Windows and Linux systems, as well as on Mac computers. So I'm just going to show on Linux and on Windows because Linux and Mac commands are rather the same. The only difference is between the Windows command prompt and the Linux terminal. So whichever system you have, whether you have Mac or Linux or Windows, you want to open terminal or command prompt. So if you're on Linux and Mac, open terminal, and if you're on Windows, just open command prompt. And the first command that we want to take a look at is the ping command. Most of you are probably already familiar with it. To ping a device, you simply just type ping and then the IP address or domain name. So for example, I want to ping google.com. I just type it in, and on Windows, it will automatically perform 4 ping requests. While on Linux, if I go here, ping google.com, it will ping as long as I let it run. So I need to stop this in order for it to stop pinging. You can see the difference. On Windows, it does it 4 times and then stops automatically. And here it will go forever until I Control C in order to stop it. And down here we have the command results, such as 16 packets transmitted, 16 received. There was 0% packet loss and the time that it took for packets to arrive. So simply you can always use ping command to check network connectivity to a specified host or to a specified IP address. It works by sending ICMP echo request packets, and it measures the round trip time. Now the next command that I want to show you is called traceroute. Now traceroute shows the path that packets take to reach a destination. It displays the list of routers and different hops between your computer and the destination that you're trying to reach. So for example, if I type traceroute, once again google.com, it should give me the exact path of hops that it took to reach google.com. So let's leave it for a second to run. And here it is. It reaches the Google's IP, which is this one, in 11 hops. And this is the time that it took to reach it. And these are the routers or different hops that it took to reach this particular IP address. Now the same command on Windows is not spelled exactly the same. So instead of typing traceroute like we did on Linux and Mac, we want to type tracert and then the actual destination that we want to get the hops for. So let's do once again google.com and let's see how many hops will it take from a Windows machine. And here it is. It shows 9 hops, which reaches the same IP address which we saw on Linux right here. So that would be the traceroute command. Now the next important command that I want you to know is the ifconfig command. So let me just clear the screen and type ifconfig, which is on Linux and Mac. It displays detailed information about your network interface, including IP address, subnet mask, and MAC or physical address. So here we have the local IP address of this Linux device. We have the subnet mask. We have the IPv6 address. We also know what IPv6 is. And we have the MAC address of this particular interface. Now, on Windows machine, the command is ipconfig. So it's not ifconfig, it's ipconfig. And it will give the exact same information. So down here we have the IP address as well as the IPv6 address. and the subnet mask. The next important command, which you might find useful, is the ARP command. Now, we already mentioned before that ARP protocol is a fundamental networking protocol that is used to map an IP address to a corresponding physical MAC address on a local network. To check the ARP tables, you can type the command ARP-A. This will display the ARP cache, which maps IP addresses to MAC addresses on your local network. So I typed it incorrectly, ARP-A, and here is the ARP cache for this Windows machine. We can see the IP addresses and their respondent physical or MAC addresses. Now, same goes on Linux, except the command here is ARP-N. So if I type ARP-N, for now it only manages to find the gateway or the router IP address, which has this particular physical MAC address and this local IP address. Besides this, we also have the command called NSLOOKUP, and NSLOOKUP is a tool that you usually use to query a DNS server to look up information about a host name or an IP address. So for example, if you're wondering what is the IP of facebook.com, for example, you can use NSLOOKUP to get that result. So it will take a few seconds, and down here it will give us the IPv4 address of facebook.com. And you can do it vice versa. So for example, if you copy this and type NSLOOKUP and paste the IP address, so you don't get much information here except the name server, and that's about it. But you will find yourself using this command quite a lot whenever you want to figure out an IP address of a certain domain. This command is quite useful. Now, another command that you will use quite a lot if you end up in the networking or cybersecurity field is the netstat command. So if you type netstat nt, this specific command will print all the active connections that this Linux machine currently has. Now, since it doesn't have any active connections, there is nothing being displayed here, but if I was to open, for example, Firefox right here and run the command again, now we have a bunch of established and waiting connections. So you can even see what is the IP address and port being used on your local Linux machine, as well as the foreign or destination IP address that we are connecting to and the port that we are also connecting to on that IP address. So you can see that once I open Firefox, we got a bunch of results of port 443 and port 80, and you will learn in just a few lectures what these two ports are used for. Now, on Windows machine, you can also type nstat or netstat-nt, and it will print the exact same result. So here we can see the established connections and the ones that are in the close wait state. So whenever you are inspecting connections, make sure to also watch the state of the connections, because not all connections are active. All right, and the last command that I want to show you is the route command. So if you type route-n, this will show you the routing table on your system. So in my particular case, it looks like this. It gives us the gateway, and gateway is simply just my router's IP address, which in this case is 192.168.1.1, but using the route command will show you the routing table. All right. Now, these would be some of the simple networking commands which you can start using for whichever task that you might need them for. These are very useful. You will use them a lot in the networking field, and you will get used to all of these commands. And once you start using them, you will also discover some other networking tools and some other less common options that you can use with the tools that we showed in this lecture. Nonetheless, thank you for watching, and I will see you in the next lecture. Okay, so the OSI model stands for Open System Interconnection Model. This model is used to demonstrate or show how communication occurs between different devices on the network. It is considered to be a standard for how different computer systems communicate with each other. The OSI model consists of 7 layers. Each layer handles a specific job and communicates with the layers above and below itself. So let's discuss each layer a little bit. We have the physical layer. This layer includes physical equipment that is involved in the communication and data transfer. These are things such as cables and switches, for example, and this is the lowest layer since data here is divided into ones and zeros, or in other words, in binary. Next one that we have is the data link layer. Now the data link layer is responsible for creating a reliable link between devices on a network. It deals with issues such as error detection and correction, as well as the organization of data into smaller packets. The data link layer takes packets from the layer above, which is network layer, and breaks them into smaller pieces called frames. The next layer that we have is network layer, and this layer is responsible for facilitating data transfer between two different networks. It deals with issues such as addressing and routing, and is responsible for finding the best path for data to travel. When we talk about packets, we typically refer to the network layer. Now, above the network layer, we have the transport layer. This layer is responsible for the end-to-end communication between two devices, and it also ensures the data is delivered reliably and in correct order. It deals with issues such as error checking and flow control, and it also breaks down data into smaller packets if necessary. Next, we have the session layer, and this layer is responsible for opening and closing and maintaining communication or connection between two devices. The time between when the communication is opened and closed is known as the session. This layer ensures that the session stays open long enough to transfer all the data being exchanged, and then closes the session in order to avoid wasting resources. The sixth layer that we have is the presentation layer. This layer is responsible for converting data into a format that can be understood by the above layer or the application layer. It deals with issues such as data compression and encryption. And the last layer is so-called application layer. This is the topmost layer of the OSI model, and it is responsible for providing a user interface to the network. It is the only layer that directly interacts with data from the user. You might have heard of application layer protocols such as, for example, HTTP or SMTP. Okay, now that we got this out of the way, let's go straight into network design and security.